interruption. So there was some technical glitch pertaining to YouTube live screening thing, I believe. So I was just going through some of the questions that you have posed over here, wherein one question was like, where do CS students find applications in terms of nanotechnology? Correct. So if you can see on this particular picture, nano computers, right? Nano chips smaller than dust particles will allow powerful computers to be carried in one hand, and all the chips, all the computer components as on today, it is completely made up of nanomaterials. So with this introduction, right, I just want to ask you people a simple question. Can you tell me who invented or who discovered this science of nanotechnology? There has been a big debate going on over this from the past centuries. That is maybe, let me explain you with that. When people talk about nanoscience, they start by describing things. Say, for example, physicists and material scientists, they point out to things like new nanocarbon materials. Correct? They are totally bothered about mechanical properties. They are bothered about electrical properties. And at the same time, this technology, the cell phone technology, whatever we are getting as of now, it is completely because of this nanomaterial by name graphene. Correct? And also you can see this nanotubes, right? So our TV screens are becoming big, whereas the thickness of TVs, televisions, they are becoming very small because of this wonderful material, graphene, right? So physicists, they claim that they were the first to actually invent or discover this particular science, whereas biologists, they start fighting with us. They counter that nanocarbon, it's a recent discovery, and they have been studying DNA and RNA since 1953, right? So these are the strands, basically the strands of DNA and RNA, which is taking the shape of a helix. Correct? So biologists, they claim that the nanoscience, the science of nanotechnology, it's a recent discovery, and DNA and RNA, it's a very, 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 very old discovery. So they claim that the discovery is based on the discovery of nanoscience was because of them. Whereas the chemists who are solely responsible for this drug discovery program, all those things and all, they've been synthesizing molecules over for a century. Correct? So look at this. In the year 1965, the first OLED stands for organic LED material. Organic LED in the sense, the TV screens, your mobile screens, all these things are made up of your organic LED materials, right? So they claim that they were the ones who actually discovered the nanomaterials. And look at this, the second one, commercial OLED material, polypyrrole, right? The molecule looks very much similar, but when you look at the connectivity, this actually is straight, whereas this is inverted. This is straight, this is inverted. That's the beauty of this. Clear? Now, most heavily investigated molecular electronic switch. Look at this particular molecule. So all these molecules, chemists, they claim that it was discovered or it was invented by them. So there has been a long debate between physicists, chemists, as well as biologists. But at the end, what matters the most is the technology that is getting improvised. So what these people are claiming, they are very, 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 very small, which means to say automatically a question will be raised. Is nanoscience the study of small things? Of course, yes. Because what is so special about a nanometer? Do you know? Steve Jobs, when he was actually trying to improve Apple, which was totally bankrupt in the year 1997, in 1984, actually he was the one who found this particular Apple company, right? But due to some technical or due to some managerial this thing, he was actually thrown out of Apple, and once again in the year 1997 he was higher, wherein in 2001, the concept of iPods came into picture. In 2010, the concept of iPads came into picture, right? So while designing this iPod and iPad, he appointed the best of the engineers and he told them to actually design a very, 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 very compact thing wherein it fits everything. What a normal phone has without security, Apple has all those things with security. So he told engineers to actually start working on it. So two engineers, they actually designed a phone. Clear? And they happily, very happily took that particular phone to Steve Jobs. Then he told, is there any space over here? Then they were very happy to say that, no, sir, there is no space left. You know what Steve Jobs did? He actually directly dipped that cell phone into water, wherein water bubbles started to come out. So if water bubbles are there, then ultimately there is space. He told those engineers, still there is space that is left inside. You please relook into the work, whatever you are being doing. So that is the reason why Apple phone, even today, it is very, very, very compact when you compare it with the other cell phones. So why I took this example was we were talking about what is so special about a nanometer. You know what a nanometer micrometer is? A micrometer is 10 power minus 6, right? Whereas, look at this. Earlier, your SIM cards would look like this. That is the regular size SIM cards. These are, your Dr. Lingya Gowda's generations SIM cards. Next came micro, right? A little smaller than what it was, and now nano, it is your generation, right? Look at the size, how it is getting decreased. Though the size was there, sorry, though the size was very big, the facilities that they were able to provide was very less. But now, since you are getting into nano, the facilities, whatever you are getting, 4G, 5G, all those things and all, it's getting improvised. All these things are happening because of nanoscience. Clear? Now, is this a science or is this a technology? Nanoscience, it is the study of nanomaterials, their properties, and related phenomena pertaining to these nanomaterials. Whereas nanotechnology, see, please understand the difference between science and technology. Science is what? It's all about the study of materials, their properties, the phenomena related to their properties. Whereas technology is the combination of physics, chemistry, biology, computers, material sciences, etc., 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 integrated with engineering, entering the nanoscale. This means to say that science and engineering focused on making the particles, things, and devices at the atomic and molecular scale. Right? So in engineering, in the language of engineering, we call it as microengineering. Again, I come back to claim that nanotechnology, it is the application of nanoscience to produce devices and products. See, say for example, all the new generation cars, we look at safety. Safety in the sense, we look at where how many airbags are present in that particular car. What exactly happens when we meet with an accident. The airbags will be compressed inside a small box, right? Due to the impact, what will happen? It actually opens. So that is exactly your nanomaterial. That airbag is exactly your nanomaterial. So my overview of the talk would be the introduction, and I'll be telling you about the synthesis of nanomaterials, wherein basically we'll be concentrating on chemical methods, the types of nanomaterials, that is, what are the different types, and the applications of the science of nanotechnology. Now, it was on 29th December 1959 at the annual meeting of American Physical Society at California Institute of Technology. one of the famous scientists, one of the famous physicists, Richard P. Feynman, he boldly put forth this: there is a plenty of room at the bottom. Even today, Feynman's lectures are actually world famous, right? He was the first to claim there is a plenty of room at the bottom, right? In the year 1965, he actually won Nobel Prize in Physics, correct? So, of course, this is to actually interest you. He was the one who told this: study hard what interests you most in the most undisciplined, irreverent, and original manner, it's if possible. Because, my dear students, take it from me, nobody will question you how you wrote the exam. Nobody is bothered about how you wrote the exam. Everybody will only be asking what is the percentile. Clear? They will not ask you whether did you actually study all night, did you actually copy, or you didn't study at all. They will be totally bothered only at the end result. Clear? Why I am telling you this is we are living in a we are living in a, we are living in a century wherein we are totally bothered about skill sets. I'm proud to say that yesterday I was actually going through a placement magazine wherein people from Adobe, they have actually hired a B or BTech engineer for around 25 lakhs. 25 lakhs was the take home, right? Why? I was actually reading their success story. Why they were able to do that was, why that particular student got selected was he or she had that extra skill in them. Extra skill. Books, definitely they are one of the very good means to actually see to it that you get a degree, but nobody is bothered about your degree. They are bothered only about what extra skill you have. Clear? So with this, if we look at the history of nanotechnology, going back to 2000 years, Greeks and Romans, they were using sulfide nanocrystals to dye their hair. And 1000 years ago, gold nanoparticles of different sizes, they were used to produce different colors in stained glass windows. You can see these colors. In 1974, Norio Taniguchi was the first person to actually coin the term nanotechnology. In 1981, IBM, it develops the scanning tunneling microscope. In 1985, that is approximately around 35 years from now, C60 or buckyball C60 was discovered by Harry Kroto, for which he won the Nobel Prize in the year 1996, along with his team of Richard Smalley and Robert Curl. In 1989, IBM logo, it was made with individual atoms. This was actually the original IBM logo. Right? In 1986, atomic force microscope was invented by Binning, Quate, and Gerb. In 1991, carbon nanotubes, that is tubes which we can actually roll it. Right? It was discovered by Ijima. Clear? So if you want to understand the concept of nanometers, look at the first picture. This is actually our Milky Way galaxy. Correct? If you still zoom it, we'll be able to see our Earth. If you still zoom it, we'll be able to see some water layers. If you still zoom it, we'll be able to see this. Correct? If you still zoom it, we'll be able to see a green colored patch like this. Zoom it still, we'll be able to see a person who's sleeping. Next, the hand of that particular person, which is around 10 centimeter. Next, still if you zoom it, that is if you still go inside, that is if you go to 1 centimeter, you'll be able to see this. 1 millimeter, you will be able to demarcate like this. If you go to nanoscale, you can actually clearly see the tissues, all those things like this. Still, if you still go further, that is for a picometer, you will be able to see this. Look at where we started and look at where we ended with. We are totally bothered about engineering these particular cells or see these particular tissues, so that it will definitely be of help for a mankind. Still, if you want to compare your nanomaterial to a single strand of human hair, it would look like this. Whereas a nanofiber, it looks like this. If you compare this with this, that is a hair with a nanofiber, a human hair is about 100,000 micrometer wide. That is, it is 100,000 micrometer big in size compared to that of a nanostrand. Right? What's the big deal about something which is very, very small? Sir, why should we be bothered about things which are very small? Why? Because materials, they behave differently at this size scale. They start to behave differently at this size scale. Look at this particular beautiful colors. Right? In all these conical flasks, we have nanomaterials. We have nanomaterials. The composition of nanomaterials, that is the amount of nanomaterials that we have put into these particular conical flasks, are different, as a result of which we are getting different colors. See, quantum dots at 3.2 nanometer in diameter have blue emission, that is this one. 5 nanometer, it has red emission, that is this one. If you change the size and composition, then definitely all these things will also change. The color will also change. Clear? To move on, look at this. Why nano will actually change the properties of materials? Why will it change the properties of materials? Any answers from your end? You can type in group chat. Why will it change? Why? Because look at the first particular picture. The diameter of this particular item is around 10 micrometer. 10 micrometer in the sense 10 into 10 power minus 6. Whereas look at this. Though this picture is looking very blurred because of the increased size. Look at this particular picture. Due to the decreased size, we are able to demarcate between one atom to the other. So this way, we'll be able to actually, clearly, understand the behavior of materials. If you come to properties of nanomaterials, nanoparticles, they tend to be more chemically reactive when their ordinary sized counterparts, because they have more surface area. That is, we'll be getting more surface area. An increase in surface area to volume ratio alters the mechanical, thermal, and catalytic properties of materials. Nanostructures or nanomaterials, they exhibit properties different from their macro scale counterparts, or in other words, we call it as their big brothers, such as mechanical strength. You know why Mercedes-Benz is so costly when you compare it with Maruti? Though both have the same, physically, Maruti car will also move, and at the same time, Benz will also move. The quality of materials that they use in Mercedes is very, 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 very strong. It's of a very high quality. Clear? Electrical conductivity. Look at the concept of your induction stoves. The material with which these induction stoves are made. Look at the concept of that, right? If we can understand the electrical conductivity, thermal conductivity, how fast the heat flows through them, we can actually study that. Chemical reactivity, how fast they react with each other to chemicals. Transparency, magnetism, and many more. Right? You actually play around with the size, the properties are going to change. Change the size, there will be a change in the property. Clear? Enough. As I was telling you, most are tunable with size. If you look at the optical properties, as you all know, gold, bulk gold, it looks yellow in color. Whereas if you go to the nanoscale, if you go to the nanoscale and if you try to see gold, it looks red. Actually, gold is red in color. The gold particles are so small that electrons, they are not free to move about in this particular thing. In a nanometer, I mean gold. Whereas in bulk gold, the particles will be free to move. Because this movement is restricted, the particles react differently with light. That is, since there will be no movement, then definitely, definitely the particles, it starts to react differently with light. Okay, look at this. This is your bulk gold, this is your nano gold. That is depending on the size. These are the sizes. This is your bulk gold, this is your nano, that is nano gold particles. Is that clear? Now, if you look at the magnetic properties, maybe in your first term you would have studied about diamagnetic, paramagnetic, and ferromagnetic materials. Diamagnetism means what? It's a property of material that opposes or that actually repels the applied magnetic fields. Why? Because the electrons are already paired. Clear? In the case of paramagnetism, they'll be unpaired. That is, it's a property of material that gets attracted to magnetic fields. Clear? Why? Because there will be unpaired electrons. Bulk gold and platinum, they are non-magnetic, but at the nanoscale, they act as magnetic particles because their movement will be restricted, right? They cannot actually run away from there. Gold nanoparticles, they become ferromagnetic when they are capped with the appropriate molecules such as thiol. Thiol in the sense, it's a 5-membered ring with a sulfur atom. Correct? So gold nanoparticles, it becomes ferromagnetic when they're capped with appropriate molecules such as thiol. And at the same time, magnetic nanoparticles, they are used in a range of applications like imaging, bioprocessing, refrigeration, as well as high storage density magnetic memory media. Right? Since the advancement of this nanotechnology, the size of our hard disks are also getting bigger and bigger. As a result of which, nanoparticles or nanomaterials, they are usually employed in data storage as well as sensing. Look at this. The size of this nanoparticle is 1 centimeter. Correct? At time t is equal to 0 seconds, if we pour nanomaterials into a beaker and if we stir it, it looks like this. 2 seconds, it looks like this. Simultaneously, you please place a magnet near the beaker. 8 seconds, it looks like this, and 20 seconds, all your nanoparticles, it actually comes and settles at one particular place. Why I'm telling you this is to actually tell you the magnetic properties of a nanomaterial. As I told you, if you take this particular first picture as the bulk gold, right, the number of atoms will be more, as a result of which it behaves like a non-magnetic material. Whereas you come down to nanoscale, what exactly happens? All the materials, all the gold particles, they are actually attracted towards the magnet, right? Now, sir, how do we synthesize all these things? From your examination point of view, this is very important, right? Physically, there are so many methods, right? Chemically also, there are colloid, sol gel, inverse, Micelis, etc. And we'll be only bothered about sol gel method. Biologically, there are biomembranes, DNAs, enzymes, microorganisms, etc. We are totally bothered about sol gel method as well as chemical vapor diffusion method. Right? Now, if you look at the synthetic approaches, the first approach would be top-down approach. That is, we have a bulk particle and we are actually going to disintegrate that bulk particle into powder, further disintegrate the bulk particle, the powder into nanoparticles, and further disintegrate these nanoparticles to clusters, and then again to atoms. It looks something like this. We call this as top-down approach. It would look something like this. We have a big rock, right? We have a big rock, and if we carve that, what will happen? We have a beautiful statue. Correct? Building something by starting with a larger component and carving away material. It's like a sculpture. That is, we have a very big stone and we are going to actually carve a sculpture out of it. In nanotechnology, we call this as lithography, or in other words, photolithography and etching away material. Etching means carving. Clear? So, in the case of bottom-up approach, we take a brick, we have a building, we can actually build a building from these bricks. This was actually top-down, that is breaking a bulk material into atoms or nanoparticles, and this actually is taking a nanoparticle and creating a bulk material. Correct? So these are the two methods. If you look at the classification of synthetic methods, see here, atoms in the bottom-up approach, you mix them with nanoparticles, it becomes bulk. Correct? You take bulk material, you break them into clusters, you break them into powder, you break them into nanoparticles, you have this. So this particular method, that is the bottom-up method, is actually highly advantageous. Whereas this, it requires a lot of, this actually requires a lot of investment and is considered to be a slight, it's a little costlier compared to this. Correct? If you take the sol gel method, please take it from me. This is very important from your examination point of view. This is very important from your examination point of view. So I'll be sharing the PPT with Lingya Gowda sir. So he'll be in turn, he'll be able to actually share that particular PPT with you. In the sol gel process, it's a very old process known since the late 1800s. The versatility of the technique has been rediscovered in the early 1970s when glasses were produced without high temperature melting processes. That is, there was an advancement in this particular method, though it was actually in the year 1800s, there was a little advancement that glasses were produced without high temperature melting processes. It's a chemical solution process used to make ceramic and glass materials in the form of thin films, fibers, or powders. Look at your mobile screen. It's a transparent screen, right? So that transparent screen is actually made up of a nanoparticle which is optically flat. Optically flat in the sense it's completely transparent. We call that to be a thin film for that matter. A sol means what? It's a colloidal. Colloid means what? It's a mixture of two types of substances which are placed together. A sol is a colloidal or molecular suspension of solid particles or ions in a solvent. Whereas if you take a gel is a semi-rigid mass that forms when the solvent from the sol begins to evaporate and the particles or ions left behind to join together in a continuous network. It looks something like this. See here. We have a sol, precursor in the sense the starting material. Hydrolysis is going to happen. We have a sol. Further, you heat this particular sol and what will evaporate it? What will happen? It becomes a gel. A gel on further heating, what will happen? It becomes an aerogel. Typical precursors are metal alkoxides and metal chlorides which undergo hydrolysis. Hydrolysis is a chemical process in which a chemical compound is broken down by a reaction with water. That is, they see to it that that particular chemical compound reacts with water and it is broken down. The chemical compound is broken down, right? The sol evolves then towards the formation of an inorganic network which contains a liquid phase that we call it as a gel. The advantages of this is it can produce thin bond coating to provide excellent adhesion between metallic substrate and the top coat. That is, it actually becomes a very good adhesion. Adhesion means what? To stick. Clear? It can produce thick coating to provide corrosion protection performance. It can also easily shape materials into complex geometries in a gel state. It can produce high purity products. That is, the purity of products will be very, very, very high. It can have low temperature sintering capability, usually up to 200 to 600 degrees Celsius. Correct? It can provide a simple, economic, and effective method to produce high quality coatings. Have you ever seen a Mercedes Benz wherein the color of that Benz is getting faded? Or have you ever seen a BMW with a faded color? It's not possible because the nano paints that they use will be of a very, 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 very high quality. Correct. So that's all about your sol gel method. If you next move to the allotropes of carbon, allotrope means what? Different structural modifications of an element. Say for example, you take carbon. We have 4 allotropes: diamond, graphite, amorphous carbon, and now we have fullerene family. Though diamond and graphite, they both differ entirely in their structure, they all are made up of a single material, that is carbon. Look at these fullerene. Fullerene is also an allotrope of carbon. The main and the most famous fullerene is C60. That was the one which I showed you. This was actually discovered in the year 1985 by Kroto and Smalley, right, for which they got the Nobel Prize in the year 1996. So this fullerene is popularly known as Buckminster fullerene in honor of the American architect Buckminster Fuller. He was the one who actually built this. He was the one who actually built this, that is Buckminster. So that is the reason why they call it as Buckminster fullerene. This is what we call. This is exactly how it looks. This is actually still there in America, and you can see one of its kind in your very much in our Infosys campus. Correct. So here what exactly is there is, it represents, that is the shape of C60. It resembles the dome structure based on hexagons and pentagons designed by Fuller. Look at this. We have a hexagon, and adjacent to it we have a pentagon. We have 1, 2, 3, 4, 5 hexagons, and in the middle of that 5 hexagon we have a pentagon. So this particular thing, it was beautifully built by Fuller in the year 1960. So which is actually popularly known as Buckminster fullerene, and this is very much there in United States of America. Right? The types of fullerenes are C60, C70, C80, and nanotubes. Why C60 means it has 60 atoms of carbon. C70 means it has 70 atoms of carbon. C80 means it has 80 atoms of carbon, and it is also called as an isomer. And a nanotube means you convert these things into sheets and you roll it, you have a nanosheet. Correct? As I was telling you, C60 is also known as buckyball, as it is a spherical cluster of carbon atoms which are arranged in a series of 5 and 6 membered rings to form a soccer ball shape. If you take a soccer ball, even that will have 60 atoms. 60 atoms in the sense 60 spots, right? Other relatively, as I was telling you, common clusters are 670, C70, C72, C74, C76, and it goes on like that. Clear? Your C60 would look something like this. Your C70 would look something like this. As I was telling you, the main difference is the total number of atoms, right? If you look at the bond structure, sir, what makes this and C60 and C70 different? the bonding pattern of the C60 fullerene with yellow bonds, that is this one, they represent double bonds, and the red colored ones, they represent single bonds. The pentagonal rings, they contain only single bonds. See here, there aren't any yellow colored bonds. Whereas if you take the 6-membered ring, we have a yellow colored one, adjacently a red colored one, and it repeats, right? The yellow bond, it represents a double bond, and a green bond, a red bond, it represents a single bond. The pentagonal rings, as I was telling you, it contains only single bonds, and double bonds have a shorter bond length and lead to the instability in the pentagonal ring. You might ask, sir, why there isn't any double bond over here? If there is a double bond present in this particular 5-membered ring, this actually will start to pull that is, these atoms will start to pull towards each other, as a result of which it leads to instability in the structure. That is, the pentagon, that is the 5-membered ring, will start to disintegrate. The limitations on double bond locations lead to poor delocalization of electrons, increasing the molecule's reactivity, which means to say, with only 6-membered rings, with only hexagons, it will be not possible for us to completely build a fullerene, that is a C60 fullerene, right? So applications, it is used as a lubricant, correct? It acts as molecular ball bearings. It is used as a superconductor when mixed with alkali metals. It is used as a soft ferromagnet, and at the same time, it is used in electronic, microelectronic, and non-linear optical devices. And if you look at the medical field, they are actually used to even inhibit the HIV-1 protease. That is, HIV-1 protease is actually the enzyme which is responsible for the development of the virus, correct? So even nanomaterials, they are used in the field of medicine to actually treat AIDS, right? Now, coming to nanotubes, as I was telling you, a carbon nanotube is a tube-shaped material made of carbon having a diameter measuring on the nanometer scale. If you can see here in this particular picture, there are no pentagons. You have only hexagons, 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 and only hexagons. You roll these particular sheets into the desired diameter you want, you have a nanotube. Carbon nanotubes, they are formed from the graphite sheet, and the graphite layer appears somewhat like a rolled up continuous unbroken hexagonal mesh, and carbon molecules at the apexes of the hexagons. Apex in the sense vertices, corners. This looks like your roll, veg roll, or whatever you eat at your place, right? Nanotubes, they are members of the fullerene structural family. Their name is derived from their long hollow structure with the walls formed by one atom thick sheet of carbon called graphene. That is, these are actually graphene sheets, right? So if this is actually the image that we have taken from a SEM, but if you take in bulk, it looks like this, right? So he was the one, Sumio Ichima. He was from Japan, and he was the one who actually discovered, who actually invented this nanotubes. That was in the year 1991, for which even he also got a Nobel Prize, correct? So nanotubes, they are basically classified into two types: single-walled nanotubes, multi-walled nanotubes. The other related structures of carbon nanotubes are torus, bipod, nanobud, cup-stacked carbon nanotubes, graphinated carbon nanotubes, and nitrogen-doped carbon nanotubes. That is, they mix graphene as well as nitrogen in two different concentrations, as a result of which it becomes a doped carbon nanotube. If you take single-wall nanotubes, they have a diameter of close to 1 nanometer with a tube length that can be many millions of times longer. It depends solely on you. as to how much long you need your single walled nanotube. You can run them into kilometers. The structure of a single wall nanotube can be conceptualized by wrapping a 1 atom thick layer of graphite called graphene into a seamless cylinder. That is, you take a cylinder, you take a sheet, roll it, you have a single wall carbon nanotube. Whereas multiple walled, it has multiple number of rolled layers, or in other words, concentric tubes. The interlayer distance, that is the distance between one layer to other, would be around 3.4 angstroms. So these are the two models, parchment model as well as a Russian doll model, in the case of your multiple walled nanotubes. These nanotubes, as I was telling you, it can be synthesized by 4 methods: arc discharge method, laser ablation method, chemical vapor deposition method, and at the end, hydrocarbon flames method. Vapor deposition method. So here initially what they do is they prepare a substrate with a layer of metal catalyst particles. Most commonly used are nickel, cobalt, and a combination of any of these three, right? Look at the temperature to which they are heated. They are heated to a very high temperature, that is up to 700 degrees Celsius. This is how the setup would look like, experimental setup would look like. That is, two gases are bled into the reactor. That is, what they do is they actually pass two gases into the reactor. A process gas such as ammonia, nitrogen or hydrogen, and a carbon containing gas such as acetylene, ethylene, ethanol or methane, they actually are fed into the reactor. So once they feed into the reactor, they start to heat at 700 degrees Celsius. Excuse. Once they start to heat at 700 degrees Celsius, nanotubes, it starts to grow at the site of the metal catalyst. That is, it starts to deposit here. The carbon containing gas is broken apart at the surface of the catalyst particle, as a result of which the carbon is transported to the edges of the particle, where it forms the nanotubes. That is, nanotubes will start to sit on the surface. Chemical vapor deposition, it's a very simple method, but it has attracted attentions for its feasibility and potential for large area production with reasonable growth rates and at relatively low temperatures. Why I'm telling you this is, if you look at the materials that we are going to get, it's only carbon, 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 carbon. Of course, carbon is highly toxic. That is the main disadvantage of a nanomaterial, of carbon nanotubes, right? If you look at the properties of carbon nanotubes, mechanical strength, they are the strongest, flexible, and stiffest materials yet discovered in terms of tensile strength and elastic modulus, respectively. Just go back 10 years. Just go back 10 years. You had your Hercules, you had your MTB, you had your Hero cycles, but you go to Decathlon now. You have cycles which are foldable. You have cycles which can be demantled and assembled very easily. Why? Because the strength would remain like that and the flexibility would remain like that, and all credits to nanotechnology. Hardness. The hardness and bulk modulus of carbon nanotubes are greater than diamond. Till date, diamond was actually the strongest of the material, which was considered to be unbreakable. But scientists have synthesized nanomaterials which are stronger than diamonds. So that is the reason why, cars of American president, Indian prime minister, even if they are blown, even if they are exposed to a high, very big explosion, nothing is going to happen, because courtesy carbon nanotubes. Electrical properties. Gone are those days wherein we were used to change bulbs because of the filament. Now we have nanotubes which has high current carrying capacity, as a result of which we have LEDs. Clear? Thermal conductivity. All nanotubes, they are expected to be very good thermal conductors along the tube. Electromagnetic wave absorption. Right? Even this electromagnetic wave absorption, it is very good in terms of carbon nanotubes. The thermal properties I have told you before. The main disadvantage, as I was telling you, toxicity. Because we'll be playing around with carbon. Toxicity. Defect. There will be open spots like this. There will be open voids or spots like this. We call it as crystallographic defect. If there is a vacancy in this particular thing, there are chances that the stability of an atom would be lost. Right? Finally, if you look at the applications of nanomaterials, these are actually nanopants, right? Wherein it is non-stainable. Correct? That is this jeans pant, nano jeans pant, it will not absorb any sort of water or any sort of liquid thing that actually falls on it. It sits exactly like this. So presently you will be actually, washing your jeans pants once or twice in a year. From now on, there is no point in actually, if you buy a nano jeans, there is no point in actually washing it. You can actually just wither it off like that. Correct? So carbon, I was telling you the concept of Mercedes-Benz. Correct? So Mercedes-Benz, it is covered with tougher, shinier nano paints. Correct? It is water and dirt repellent. That is, I'm talking about paints over here. It has brighter colors, enhanced glass in the future, could change color and also self-repair. Buildings. That is, paints on buildings. They are actually designed in such a way. You might have seen Shah Rukh Khan and so many celebrities advertising for paints. They are actually nano paints. Solar cells. They are planning to actually implement this. Solar panels on cars which can actually absorb heat and self-drive. Because that is the only cheapest form of alternative energy that we have got as on today. In medicine, nanotechnology is playing a very, 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 very vital role. Correct? Say for example, look at this. It is used in pharmacy, it is used in visualization, that is your optical specs. It is used to treat cancer, it is used in diagnosis, it is used in surgeries. One example, look at this. This is actually a nanomaterial. That is quantum dot injection is what they have done. Quantum dot injection is what they have done. What they do is they actually inject that particular thing to a mouse. What will happen? It grows like this. Right? If it grows like this, can you make out the difference? Here it is red, here it is green. Right? Live cell imaging. That is, we can see how exactly a drug is actually reacting in a particular in treating Alzheimer's. This is Alzheimer's brain. You know what do you mean? What Alzheimer's is? Alzheimer's is actually memory loss. They will not be knowing what it is, where it is, and how it is. They will even forget their kith and kins, their parents, their kids, everyone. But if treated with nanoparticles, that is gold nanoparticles, an Alzheimer's brain, it can be cleaned into a healthy brain. That is, gold nanoparticles can be functionalized to specifically attach to aggregates of this protein. That is, it kills the cells which are responsible for Alzheimer's, and you have a healthy brain. Right? So here, as I was telling you, the patient, an Alzheimer's patient, he or she forgets whether had they taken drugs, medications for that matter. This is before irradiation and this is after irradiation. Alzheimer's before irradiation, that is Alzheimer's after irradiation. That is, an Alzheimer's cell that is after irradiation. In healthcare, as I was telling you, lot of cells and tissues every day they die in our body, which includes even neurons also. Cells and tissues, it will be possible for them to actually rebuild themselves. But if a neuron dies, neurons are actually responsible for us for the movement. You raise your hand, you raise your finger, it's because of neurons. Correct? Right now, research is in to search a neuron grown on a chip that records the neuron's activity so that it can be reversed back. That is it. The concept of stem cell comes into picture, right? Graphene for drug discovery. The picture tells you all. And quantum dot. Earlier we had this type of televisions, and now there is a huge improvisation. Here, it finds its applications everywhere. Nanomaterials, as on today, without a nanomaterial, it becomes impossible for us to live without it. So these are some of the places wherein it finds its applications in electronics, in nanoelectronics, microscopy, atomic force microscopy, scanning tunneling microscopy, batteries, capacitors, DNA sequencing. Everywhere you have nanomaterials playing their role everywhere. See here. This is actually the list of top 20 nanotechnology products. The materials will be wrinkle-free. Wrinkle-free shirts are already, wrinkle-free fabrics, they are already in the market. Right? These are some of the sporting goods. As I was telling you, it has become costlier because of the flexibility in the materials, right? With this, I end my talk. Hope I have made you people to understand the importance of nanotechnology and the methods of synthesizing nanomaterials. If you have any questions, I'll be happy to answer you people. Over to you, madam and sir.
Thank you, sir. It was indeed very informative. We would look forward for your cooperation in future times also. Thank you very much.
If the students have any doubt, I'll be able to answer them.